Okay, our next speaker is Nora Newcombe. The title of her talk is Defining the Core in Core Knowledge about Geometry.
Okay, well, something must be in the air about changing one's title. This is the original title, and the abstract that's in your packet touches a little bit on a debate that Spelke and I have had about the claim of a geometric module. But I'm actually not going to talk about that to any great extent, and the one tiny bit that I'm going to touch on it is on a part of it that we completely agree on. So instead, I think a better title would be this. So I have a second title slide, Defining Core Knowledge and Relative Magnitude Estimation. So what I want to talk about today is the kind of task that you confront if, say, you're a child and you're told a story about a farmer who's trying to collect his chicken eggs. And of course, most chickens don't provide maps by which a farmer could find their eggs. But say they did, there's a little map, and the farmer could be aided in finding his eggs by using the map. So the eggs are a certain distance, say in a circular field from a tree or from a little house or something like that. And you would have to scale from the small circle map to the larger sort of farmyard in order to find the eggs. So this is a familiar problem. We all use maps, we all scale distance. We all encode distance, even in an absolute sense, even when we don't scale it. And this is an important ability. Or on the right, you could be asked, which of these buildings is taller, which of these views zooms in on that array of buildings, and which is the zoom out at those array of buildings. There's many tasks in everyday life in which you're asked to estimate various kinds of magnitude. So there's many dimensions of magnitude. So I wanted to begin actually by previewing my conclusions so that you know where I'm going to be headed as I tell you, this study and that study and whatever. I think it's always nice to have a guide. And what I want to say is that in my view, magnitude estimation is something we could call core knowledge. That it's initially relative, and I'll say what I mean by that, and that it's also initially, interestingly, cross-dimensional and cross-modal. And that core knowledge can support basic scaling and many basic judgments of proportion. But there is still development in various kinds of ways. And this is where I think the story of language and culture comes into play in interaction with core knowledge. So development consists not entirely in, I think there are other lines of development that I won't have time to touch on, but at least in part, supplementing perceptual strategies with formal systems, such as measurement devices and formal calculation, differentiating dimensions of magnitude, which remember are initially cross-dimensional. So initially you don't really know which dimensions you're supposed to be abstracting and separating, and you have to work out how to do that and what the domains of relevance are. And thirdly, in very substantive domains, such as when we teach people about geologic time, which is immensely longer than anything we have ever experienced or will ever be able to experience, how do you cope with these things that are outside of your ordinary experience? So I want to begin with studies that are unimaginably old. Study that was published less than 20 years ago, but it was done more than 20 years ago. The second pilot subject was my son, who was at the time 14 months old and is now a 24-year-old graduate of Wesleyan College. So this was a long time ago. Jane Ellen Huttenlocher and Elizabeth Sandberg and I did these experiments in a sandbox, basically because Piaget claimed that children had no knowledge of metric distance until they were 5 or 6 years old. And actually, there's elements of this talk that are going to come full circle, because later I'll talk about one of the reasons that Piaget gave for that is that they can't measure until that age, even not just using a ruler, but even, say, using their hands to compare mountains. And that seemed to us a kind of very strict criteria for what you might mean by judging distance. So we hid toys in sandbox that was 5 feet long and 1 foot wide. We turn the child so that the child can't just fixate the spot on the sand that the toy disappeared into, or strain towards it. We smooth over the sand so that if naive adults say, where did you hide the toy, they can't find the toy, there isn't anything that marks it, and we let the child look. And sometimes we move the child to the side and all that. I mean, there's many, many controls. And when you see a plot of the actual inches, sorry, this is the United States, so it's not centimeters or whatever, inches from just measure from the left side, measure from the right side, doesn't matter, measure from one side that it ought to be, and the y-axis is where the child actually first touched the sand. They don't always successfully dig, so what we score is just the first touch of the sand. You see that the actual responses are incredibly close to what would be perfect responding, which is to be on the diagonal line. So this seemed like pretty good evidence that toddlers who were 18 to 24 months of age did indeed encode distance, contrary to what Piaget had suggested. So we went ahead and did some experiments with infants and with looking time, in which, and this was not a communicative situation, this was a disembodied hand emerging from behind a curtain, and didn't actually wear a glove, but it didn't wear any rings or anything. So it's just hiding something in a sandbox, and there's a 40-second delay, and it digs it out of the same location. This is not habituation, this is violation of expectations. So the same thing happens for 4 times, in, out, in, out, in, out. And then for experimental babies, the hand emerges. The experiment moves laterally, so the hand looks the same, and it digs the same toy. Of course, there are 2 toys, one of which has priorly been hidden, out of the wrong location. And the child reacts whether you measure just the length of the first look. The experimental babies differ from the control babies. Or if you measure the total amount that they look over a 40-second period, you get then a crossover into action. It doesn't really matter. The experimental babies differ from the control babies. And again, this is only one experiment. There are many, many experiments. This is the same kind of finding that many, many other people have gotten. So 5-month-old babies do encode the metric distance in the sandbox. Now there are some limitations on this. So for instance, what I brought up when I asked the question of Siegler is that in this particular circumstance, the babies actually don't care if the correct object, say it was a transparent Tic Tac box with beads in it, emerges. Or if instead, as long as it's from the location that they saw something buried, instead a pink and purple cat toy with a jingle bell emerges, which they can easily tell. I mean, you could show in control experiments. They can tell the difference between a Tic Tac box and a cat bell. I couldn't believe some reviewer C maybe do this experiment, but it is true. But they can't tell the difference. There are some other limitations, so I won't show you the data, but they can only remember one thing at a time, one location at a time. It's not until well towards the end of the second year of life that they can remember 2 locations. They also, even with only one location, they can't remember it if you take them out of the situation for 2 minutes and bring them back. They have no idea where it was hidden. So this is fragile, but it's definitely there. And I just wanted to show you, because it will come into play at the very, very end in a speculation that I want to advance, something that we showed at the time about hierarchical coding. So the coding is not only metric, it's also categorical. And initially the category is it's in the box. The category is in the box. And what you see on the left is basically just a replotting of the data that I showed before, where things are holistically on the diagonal. But now I've shown the diagonal has become a horizontal line, the y-axis has changed so that I'm looking at error, and what you can now see more clearly than you could see it before is that the errors on the left side of the box are towards the middle, on the right side of the box are towards the middle, so the prototypical location of in the box is the center of the box, and things move towards the center. Now, it takes a while. In fact, in the large in smaller spaces, it takes less long. In larger spaces, it's not until 10 years of age that children start to show what adults will show, which is what I call the double squish. So they've divided the box into the left half and the right half. There's a center of the left half, a center of the right half, and things things migrate towards those two different prototypes, which has the consequence of making you considerably more accurate. I mean, you were pretty damn accurate on the left, but you're incredibly accurate on the right because you have two prototypes to be attracted towards, but also giving you a quintic function. And I used to joke that I never hoped to predict and never hoped again to predict and find a quintic function. But my last slide will tell you about another circumstance where one finds one, and I'd like to think together about that. Okay, so one thing that is slightly obscure, but I kind of love this because there are people in the world, most of them I think not in this room, but who believe that all of these experiments have to do with just a sort of dynamic systems account of what they call looking dynamics. So it has to do with where the infant's attention is attracted, and it's really a sort of artifact. And that also a part of this criticism is that we're teaching kids in the context of these experiments. So baby comes in, 5 months old, doesn't have a clue where anything is, what's going to happen, who knows, and you show them, albeit only 4 times, goes in here, comes out here, goes in here, comes out here, and they learn, oh, goes in there, comes out here, and so, of course, they're smart, they've learned what you taught them. And that should predict that if you show them 4 or 5 times, goes in here, comes out here, they should learn that equally as well, because why not? It's a perfectly sensible rule. It isn't what happens in the real world, but it's a perfectly sensible rule. So if you come not expecting anything in particular, you should be able to learn that as well. And what we showed in experiment 1, it's a little difficult to see, but the crucial application of what we found before is that the filled triangle is higher than the filled square, which is that if it comes out of the wrong location, they think, oh my goodness. But if they've been, quote unquote, taught that if it goes into one location, it can come out of the other location, and then it doesn't, then whatever, you know, who knows what's happening here. And so we haven't taught them anything. And we actually did it again in a situation in which they couldn't see the sand. So now the looking dynamics are exactly the same. And yet there's no particular reason to expect anything at all, because if it goes into an empty container, it can roll around. And in fact, this is a totally null finding. So this shows both that babies expect that sand contains things, which is itself a sort of interesting finding, and also that it's nothing to do with the looking dynamics. So whatever it is that babies know at 5 months and wherever it comes from, they bring with them to our lab. We didn't teach them anything. Okay, now, there's also a very, very long history and some kind of controversy about this, but at this point I really don't think there's controversy. I think there's really an overwhelming amount of evidence that infants' quantity estimates for a variety of kinds of quantity follow Weber's law. And you've already heard about this in prior talks. So for number, among other studies, these are, sometimes there's only one study, but sometimes there's many, many studies, so I didn't want to cram them all on the slide. Among others, there's the Jew and Spelke study. The illustrations are actually for size and area. So this is the Brannan, Lutz, and Cordy study, where they looked at the size of Elmo's face. And there's a 1 to 4, 1 to 3, or 1 to 2, or a 2 to 3 difference in the area of Elmo's face. And babies whose age I momentarily forget, but it doesn't really matter, do discriminate the 1 to 4, 1 to 3, 1 to 2, but they can't discriminate the 2 to 3 ratio. This has also been shown for time, and very, very recently for speed, which I think is interesting, because speed is itself a ratio. So what we're saying is that babies can discriminate some ratios of ratios, but not all ratios of ratios. So that's part of the story, but an even more interesting part of the story is the story about there being a generalized magnitude system. And this is where we get to the sort of cross-modality and cross-dimension aspect of this. This was discussed probably not for the first time, but sort of at this point classic citation is Vincent Walsh's piece in Trends in Cognitive Science. And there's a much more recent piece in TICS by Jacob, Valentin, and Bieder that deals with sort of neurological substrates that support this kind of judgment. Now, in what I consider really quite an interesting coincidence of people publishing basically the same finding, but with different kinds of paradigms at virtually the same moment, we have these 3 studies, Hevia and Spelke, Lourenco and Longo. Those are the 2 that are pictured. And then also Srinivasan and Carey, which I could not cram on the slide. The left is Hevia and Spelke, and the right is Lourenco and Longo. And so what this experiments show is that babies who are expecting things to be getting more and more numerous, or less and less and less numerous, also expect that things are getting longer and longer and longer, or shorter and shorter and shorter, or vice versa, et cetera, many sort of manipulations thereof. Or what Stella Lourenco and Matthew Longo did, which is the same but different, is they taught babies that if things are long, they're going to be black with diagonal stripes. If things are numerous, they're going to be black with diagonal stripes. Then they're surprised when things turn out to be short with diagonal stripes, or less numerous with diagonal stripes. Whatever, I'm taxing my short-term memory here, but you get the idea. So this is the one and only slide that concerns the findings from the geometric module research. And what you see on the left are findings from Hermer and Spelke. What you see on the right is an overhead shot of actually an apparatus that we use to test mice, but it doesn't much matter. I mean, obviously, when you test kids, it would be a little different, but since there's no indication here of scale, it could be testing kids. I mean, who knows? So there's a rectangular enclosure. The child or the mouse or whatever is disoriented. And in the case of the child, the toy's been hidden. In the case of the mouse, food's been hidden. And the question is whether the child or the mouse can find the toy or the food. And what they can do, and this is in the absence of any other cues, is to, if, say, the correct corner for the toy or the food is where the long wall is to the left of the short wall, they can zero in on the 2 corners where that's true. They obviously can't choose better than 50-50 because there are 2 corners of which that is true, but they zero in on those corners. So this shows that toddlers can compare the lengths, one is longer and one is shorter, and also that they can order those lengths so that one is to the left of the other one. This has been found again and again and again for a wide variety of species. So in my mind, what this relates to is a series of experiments done by Huttenlocher, Duffy, Levine, Duffy, Huttenlocher, Levine, Vasilyeva, Duffy, Huttenlocher, some with infants, some with toddlers, some with elementary school children, which suggests that this kind of coding of continuous distance or length is relative, which is what this is. This is relative as well as ordered in terms of what's to the left and what's to the right of the other one. So whether you're doing infant looking time or various sort of toddler and preschool and early elementary school production tasks, children succeed when the length is displayed in relation to a frame, or when the length is displayed, the red length is always what you're asked to in some way judge, relative to some other kind of standard. But if it's presented in isolation, they really can't judge its length. They have nothing to compare it to. It's actually not until 8 years of age that you can succeed in the case where it's alone. Now, of course, in some sense, length is always relative, because unless you have some indication of scale, you don't really know what you're looking at. But presumably, what by the time children are 8, they learn to do is to look around for whether it's the frame of the computer, or something like, oh, how many thumbs, or they establish some sort of crude way to have a relative standard when no obvious one is offered to them. Now, this kind of relative coding, this kind of perceptual estimation, well, it's kind of a quarter of the way up, or you look at this thing and maybe not a quarter, maybe it's a third of the way up, something like that, is sufficient to support simple scaling and simple situations. So this work, I actually have been involved with at least 2 of the 3 studies with Marina Vasilyeva and Jane Ellen Huttenlocher. in which again over a variety of ages, this time concentrating on late preschool and early elementary school, we've shown that by the age of around 3, children can scale from a small strip of paper to the larger sandbox or vice versa. That's really only along one dimension. And then, not really at 3, more by the age of 4, a little older. This is from the Vasilyeva and Huttenlocher study. They can do 2 dimensions, so there's a variety of things that are probed, and you have to translate it to either a small scaling factor or a large scaling factor. You can see that both 4 and 5-year-olds succeed with a small scaling factor. When the scaling factor gets larger, this is error, mean distance to the true location, so the 4-year-olds are not as good as the 5-year-olds. So there's a gradual emergence of the ability to do this kind of scaling. Still in all, it's pretty impressive when you consider that in sort of the task that Judy Deloach has used, it's not until the age of pretty much 3 that children even realize that one thing can stand for another. So, this little Snoopy house stands for this big Snoopy house is an obvious prerequisite to being able to scale at all. And they can scale, not quite from the first, but maybe 6 months after they can know that the small Snoopy house is the big Snoopy house. They're applying these kinds of scaling factors. And yet, Andrea Frick and I actually put all this together because I'm kind of making inferences from scattered studies, and you're theoretically not supposed to do that. So we did this all in one study, and we have the data that you see on the right, where you see that 3-year-olds can kind of do this, but not very well. And in fact, they can't even do the one-to-one very well. So their ability to copy from one-to-one is not very good. The error bars are enormous. The scaling is there, but it's not wonderful. And it improves progressively. Now, adults are not perfect, but there may be floor effects there, and it's possible, it's not for sure, that there's always some cost to scaling. And that, in fact, this is why adults have, at some point, invented the cultural conventions that allow us to scale accurately. I mean, you wouldn't want your architect who's designing your new bathroom to be subject to this degree of error. Okay, so the University of Chicago group has also looked at the development of proportional reasoning. Now we're talking about kindergartners through 4th graders, so we're talking about pretty old kids relative to some of the core things that we were talking about earlier. And this is where I get to the idea that these different dimensions have to be sorted out. So this concerns, a bear who, wants to have a certain amount of juice, and this is the amount he likes, so how do you make him have the amount of juice that he really likes? And in some cases, the bear's desired juice is just shown in a continuous format, and sometimes it's shown with marks that, for us, would help us. I mean, after all, we can count off, and then we kind of know how much. But that's keeping in mind, of course, that 3 out of 9 is 1 out of 3, which is the kind of thing that, we know proportional reasoning and fractions and things are actually not introduced in the US until 4th grade, and that are quite difficult. And in fact, what children often do is count, but then they make improper use of the counts. So if the bear likes 3, then, well, he likes this one, because there he gets 3. I mean, why not? I mean, it makes a certain amount of sense. He likes to have 3 things, and there's 3 things. So what we see is that for kindergartners, 1st graders, 2nd graders, and even 3rd graders, there's that kind of a difference. And in fact, you see that the kindergartners and 1st graders and 2nd graders are not significantly better than chance when you give them these seductive numbers. The numbers are very, very bad for them. At 4th grade, they are better than chance, and by 3rd grade better, and by 4th grade, there's actually no difference between the two. Now, in a follow-up, Ty Boyer and Susan Levine have shown not only that, again, they get the difference between the continuous condition and the discrete condition, but that it's affected by the scaling factor. So again, this is error, so higher is worse. You're especially bad when there's a ratio of 1 to 3, or this is a different ratio of 1 to 3, it just goes in the other direction. And it moves towards 1 to 1. There is no actual 1 to 1, but these are the 2 that are closest to 1 to 1, and they're usually better. So it seems that there's an intuitive perceptual strategy which is used rather than the exact mathematical reasoning which would get you all the way home and correctly. And in fact, Venke Moehring and Amir Frick and I, and this is a first experiment, I'm going to do many, many more, believe that adults may even sometimes use this. So, I mean, why not? We do estimate things by eye. And with the circle, just initially, but with the rectangle, all along the scaling factor from 1 to 4 down to 1 to 1. Adults will take longer when the scaling factor is greater, indicating that they probably need to scan across to get to what they're going to consider the correct answer. This is actually somewhat similar to many of Steve Koslin's very, very, very old experiments on imagery. That longer scanning time takes longer. So, we do eventually supplement this with a formal system. And that is the transition that one wants to support in school around about 3rd, 4th, 5th grade. And by the way, at least in the United States, the national body that recently made recommendations about mathematics education identified knowledge of fractions as the critical limiting factor that seems to be the gateway to, you thought pre-algebra and algebra were the gateways, fractions are the gateway to being able to master pre-algebra and algebra. So fractions are really a very important sort of educational transition. But even prior to that, children shockingly have trouble using a ruler. Most parents and most grade school teachers don't understand this. This is an actual item from the National Assessment of Educational Progress, NAEP, in which children are asked, how long is this little piece of crayon? Now, of course, you and I know that the correct answer is 3. 7 is truly a bizarre answer, which has no rationale for it. Many children make what's called the read-off error, which is just say, whatever it is, you look at the right-hand side and you read the number, and they will say 5. That's generally an error in the first years of elementary school, but 4th graders are still very prone to make the hash mark error. So what they do is count, but they don't know what to count. What is the countable here? They count 1, 2, 3, 4. There are 4 hash marks, so they think that the little bit of crayon is 4 units long. So again, I think this is a clash between what am I counting? Am I counting number, which I learned to count, and that seems like a good thing to count, or am I counting units of distance, and how would I know which to do? Susan Levine's group has actually done some intervention along this line. There are many interventions that teachers already use. I mean, teachers are not stupid, and they think that something needs to be done here, and they use little units, and they ask kids to measure with their fingers, and they do lots of things. But it doesn't work very well. We know that the NAEP shows that lots of children still make errors. So what Susan and her group have tried to do is to use a kind of systematic manipulation of either these clear plastic chips or gestures. This gesture represents a unit chip. And so they crossed using unit chips versus gesture with using it only at the left side of the ruler, which is sort of reinforcing all the bad tendencies in the world to only do the left side of the ruler, with the unaligned condition. And what they find is that you have to shift. Whether it's gesture or units, no matter which way you look at it, you have to teach them directly that from 2 to 5 is 3 units. Whether it's these units or those little chip units, you have to teach them units. And that actually endures at least a week later. I mean, one would like to do a little longer term follow-up, but it doesn't vanish within a week. And we've also done some research with this truly challenging situation of understanding geologic time. Now, creationists don't think geological time is a problem, but if you aren't a creationist, then it's an unimaginably long time. And it's not helped by the fact that geologists represent this unit of time as just as long in space as these other units of time, inviting the inference that this amount of time is equal to the other 3, that they divided the history of the Earth into these quarters. This is not true. This one is much, much longer than all the other ones. But geologists don't really care about it because they don't know almost anything about it, so they don't see any point in taking up a lot of space on the page since they have nothing to say about it. But people get completely the wrong idea about it. And in a manipulation that we've done, which I won't take the time to tell you about. It does work. The intervention group is doing a bit better than the control group. You'll note they aren't doing hellishly good, so we're trying to work on this to get them better. So this is the slide that I promised for the very end, which is something that I'm just starting to think about, which I don't have much to say about. I just want to mention that Bob Siegler and various colleagues, and John Opfer and my colleague Julie Booth and so on and so forth, have done research showing that linear number estimations, what you'd like to see are these linear number estimations. What you get instead initially are these logarithmic ones, where children know a good amount about 1 through 10, but they know nothing about 11 through 99, and then later they know something about 1 through 90, but they know nothing about 101 through 999, and so on and so forth. Hilary Barth has a competing explanation of this kind of data, in which she suggests a kind of power law, a cyclic power law, which gives you the data that's shown there in the upper right. That's from one of Hilary Barth's experiments. And the criticism that Siegler and Opfer make of the Barth cyclic power law is that it overfits the data. I actually don't think it overfits the data, because you get that pattern again and again and again. But I especially don't think it overfits the data because it's that quintic function. And there it is again, my goodness. And where I differ a bit with Hilary is that the cyclic power law, in my mind, is a description, not an explanation. And I think what this kind of framework provides is more of an explanation, which can, of course, be mathematically fit by a cyclic power law, which is cool. But that what you're really learning is dividing, whether it's from 0 to 100, 0 to 1,000, 0 to 1 billion. Now you're talking real money, whatever. Into halves, into quarters, so that you can use some known landmarks to really get the shape of the number line a little straighter. So I'm just back to my conclusions, except now I have to say preview of conclusions, so I say conclusions. And I'm sorry I took 1 minute and 58 seconds too much.